All right. Now, to kind of give you a heads up on where that's going for this one, we're going to go back through everything. We're going to go back through everything that I've taught you. We're going to reinforce everything. So if the first test did not go well for you, that's okay. We're not going to, like, it's not behind us, it's in front of us. We are still in it. We're going to go back through every single topic in order just about, but now we're going to do it as the textbook does. We're going to start building up a logical mathematical argument starting from the most basic principles that we use the most often, working our way on up as we start to get more and more techniques and exposure to more and more problems. But that means that you have more and more things to consider. Like, for example, functions. We talked about functions. We feel pretty good with graphs, right? But the question is, if I say function, are you thinking linear function? Are you also thinking quadratic function? Are you also thinking cubic function, polynomial function, logarithmic function, exponential function? For those of you who took trig before, are you thinking trig function? We're not going to cover trig. I'm not testing you on trig, but for all of the purposes of what we cover here, if I say function, I'm saying that I'm thinking of all of those. And I'm running the logic through every one of those scenarios and more. Any piecewise function, any squiggly line that I decide to draw on a graph paper that passes the vertical line test. Those are all functions. So we've got to go back through and we've got to say, do we understand all of those functions and how this concept works with all of those functions? And this is where if we don't understand the story, we're going to hit a barrier because there's just too much to consider without you bringing the question to me. I can't teach you all those scenarios. Again, you've got to bring those questions to me. So we're going to start with two that are very, very prevalent in the business, marketing, and real world spaces, exponential and logarithmic functions. Now, these are underappreciated by far, but what we will find is that they have a very, very key place in stories of growth, which ties very closely to money, populations, and overall spread of ideas. So anybody here who thinks that at some point in the future, they are going to utilize and or interact with social media for a business perspective, that's an exponential pattern. Like, we live in an exponential world, and therefore we live in a logarithmic world. So we're going to start enforcing all those ideas. All right, so the greatest shortcoming of the human race is our inability to understand exponential growth. Exponential growth has also been called, or at least compound interest has been called, the greatest force in the universe. Y'all want to guess who that quote came from? Not this one, the one that says the greatest force in the universe. Close.
Einstein?
It's Einstein. So if we're talking about people who understand what's happening, like, for him to say, like, the person who understood and discovered that, like, we have an entire fabric that connects our universe, to say that the most powerful force is exponents, we should listen. It's a big thing. It's a big thing. And if you can harness it, it works very strongly for you. All right, so historical origin. Let's go back to Archimedes. Archimedes, right? My guy Archie. All right, Tony Stark of the ancient age, building a bunch of engineering contraptions, doing some science, also doing some math, right? So we've got Archimedes, who is exploring math, exploring science, exploring engineering, and interested with big questions. One question that came up was the question of, how much is a big number? Now, we've got to remember a little bit of the history, right? We're living in a time when numbers are demonstrated by Roman numerals or equivalent, and people did not have a need for big numbers. Most people believed that the biggest number is what they called a myriad, and a myriad was about 10,000, okay? And people would argue, why do I need to learn math, this thing that deals with big numbers, if I've never touched anything bigger than 10,000 in my life? Right? Maybe some of you have had a similar argument with a math teacher in the past, like, why am I ever going to need to know this? Right? Archimedes is over here going, you know what? Let's take an example. Like, people say, how much sand is on the beach? People of his day were saying an infinite amount of sand is on the beach, right? Because it's tiny, impossible to count. And Archimedes says, you know what? Instead of accepting that, I'm going to calculate how much sand would fit in the observable universe. And he got a number for it. And since it was a number and it was not infinity, he was able to tell everybody to go shut up, because he could actually put a number around what they thought was the biggest idea. So the whole idea of saying it is infinity, no. It was a number. We can pin it down. It's within our ability to control and demonstrate. And he did this by saying, okay, how much sand would fit on just like going across your pinky nail? How many particles would that take? And then how many pinky nails would it take to be able to extend across an arm length? And then how many arm length, and you extend the model. You go from something you can understand to something bigger and bigger and bigger. And he published his work in what he called the sand reckoner. He was able to show people that numbers, big numbers, can be written easily and work through logically. So we can credit Archimedes for the very first exponents because that's really what he created. Let's talk about some big numbers. Let's get this well understood. We think we understand big numbers. I'm talking with some people that are like, x goes towards infinity, so I'll plug in 100. Let's understand how different infinity is from 100. First, let's start with 1,000. 1,000 is how many people are normally in a city, right? We can kind of count that in thousands, unless you're talking about really big cities. Big cities, we might go up from there. Millions, right? We can talk about Chicago. Chicago has a population in the millions. New York has a population in the millions. What is a million? A million is 1,000 thousands. That means 1,000 regular towns are all crammed together in one city, right? We start to get an understanding, 1,000 thousands. Billions. Billions, thousands of millions, 1,000 millions, line them all up. So we start talking about things like, I don't know, what can we measure in the billions? Like, what about the net worth of Jeff Bezos? All right, that would be in the billions. All right, let's do a little bit. Here's an idea. Let's take a dollar bill, and let's stack them sideways against each other. Let's do that for $1 billion, billion with a B. That's going to go across the earth, across the equator 200 times. That's how much $1 billion is. However, there's going to be so much left over at the end of that that you can then take those dollars, stack them long ways, and they will go back and forth to the moon 10 times. Billion is big. It's a big number. We're not even close to done. Paid $1 million an hour, right? How many here would get $1 million an hour? We would take that job. Do you know if I paid you $1 million an hour, you work from now until retirement, you would still not have as much money as Jeff Bezos? Like you can run the numbers. You can run the numbers, right? $1 million an hour times 40 hours a week, times 52 weeks in a year, times 40 years of work. You're nowhere close. $1 million an hour. Big numbers. It's hard to fit them all in our head. What about a billionth second? I'm coming up on mine. It'll be about a year. I'll have to celebrate my billionth second. Neil deGrasse Tyson did it with a very small amount of champagne. Real quick sip and then called it. I'll see if I can do the same thing. Trillions. That's a million millions, right? We start to get a lot of zeros here. Notice the notation that I'm using. It starts to get exhausting to count the zeros. So we start to write 10 to the 12th. That means 12 zeros. It means 10 times itself 12 times. And every time you multiply it by itself, you get one more zero. So we start to get this notation. Scientific notation starts to deal with numbers like this. Right? This is going to be the number of seconds since cave dwellers were first drawn on the caves, which makes sense because if my billionth second is about my 31st birthday, then 1,000 billions would be 30,000 years instead of just 30 years. So we talk about a huge jump in magnitude here. Quadrillion, right? It's the number of sounds and words ever spoken. Ever spoken could be measured in quadrillions. Quintillion, right? 5,000s of millions. It's the number of grains of sand on the beach. This is what Archimedes was able to calculate. Sextillion, right? Number of stars in the observable universe. How many here are in chemistry right now? Anybody taking chemistry? Anybody take chemistry in high school? Anybody here ever hear about a mole? 6.022 times 10 to the 23rd, right? So that's the number of atoms in 1 gram of whatever it is, or of that atomic weight of stuff, right? Atomic weight to measure is the same amount in grams, about that level of magnitude. In other words, there is more molecules of water in 1 glass of water than there are glasses of water in the entire planet. Right? Big, useful. All right. What about 10 to the 81st power? How many zeros would that have? 81 zeros, right? Nice and simple away, right? The number of particles in the universe. Why would we need to go bigger than that? That's the number of things we're made up of, all across. Well, we could start talking about the number of ways that we like to combine those particles. So we could talk about 10 to the 100th. That's a nice little number. We call that a Google, right? Some of you have seen that as a misspelled version of a search engine, right? That's where they got their name from. If you now talk about 10 to a Google, how many zeros would that have? It'd have a Google zeros, and it would be more than you could write out because it's already a bigger number than the number of particles. You couldn't even find enough electrons to be able to write a zero on each one and then still have it work. So what we have is this idea of magnitudes. What I want to get you comfortable with is that exponents are counting in magnitudes. We're not counting in steps anymore. This topic is about counting in magnitudes. So for that reason, if I all of a sudden say, what's the difference between 10 and 100? That's one magnitude difference, one extra zero, but it's only about 90 for a difference. Versus if I say the difference between 100 and 1,000, that's still one magnitude bigger, but arguably we would all much rather get $1,000 versus 100 as compared to 100 versus 10, right? So it starts to become a bigger difference for every single step. So we got linear growth. This is what we're familiar with for the most part. Linear growth, right? Things are going up steadily. So we can look at things like how much am I changing in each of these, and maybe I'm changing by plus 30. So I've got plus 30 at every single step. If that continues and I graph it, Descartes will show us that it is a line. So we've got linear growth, constant step change. Quadratic growth. We explored quadratics as our other kind of simple model. Quadratic growths are not where every step is the same, but the change in those steps are the same, right? So for example, we said that we could always look at these as being parallel back to the triangle numbers, that I'm going up by the odds. Well, the odds always have a difference of 2. So the quadratics are saying it's not the change in the steps, it's the change of the change that is constant. Wait, hang on, change. We've talked about change in this class, haven't we? What's the calculus concept for change? Derivatives. So it's almost like saying if I have something that is of the form x squared, that if I do a derivative to it, through the power pattern, I got 2x, which is linear growth. Hey, like this, changing by a line. And then if I then did another derivative on top of that, I would get a power pattern that brings me back to 2, which is a constant growth. Oh, that's like the change of my change. So now you all have a way of going out in the real world and recognizing if something changes as a quadratic. You look at its change, and then you look at the change of that change. If it has a level settling point for that second layer, then what you're looking at in the first layer is a quadratic. Has to be. Exponential growth. Now we're talking about magnitudes, right? Every step is via multiplication. So we're going from 3 to 9. That's going to be times 3, times 3, times 3. And we have this compounding, right? Just like we brought up when we were talking about E and finances, this multiplication over and over and over again. Okay. As a quick reminder, we can always graph these. Graphs will become very, very useful for us for being able to reference these functions and being able to determine things like limits and change and area. So as a reminder, if I have 2 to the negative second, what does that mean? 1 over 2 squared. Who can tell me why? Not just I saw it in a rule. Who can tell me why that makes sense?
Because like a positive exponent is getting bigger, so negative would be getting smaller.
We could look at it as an extension of a pattern. I like that. So let's go back down here. Let's look at this as 2 to the first. Do we all agree that that is 2, but only one repetition of 2, only one instance of 2? All right, that's the notation. 2 squared. That is 2 multiplications of 2, right? And then 2 cubed would be how many multiplications? 3. So that gets us 8. Now let's jump to the negatives for a moment. If I read this as a story, it becomes very clear why this makes sense. Because if 2 squared means repeat multiplication with 2 times, let's just translate this into its story. We still have repeat multiplication with 2, but now instead of 2 times, I have a -2. My word for negative is opposite. Can we all get behind that? We feel pretty good that negatives are opposites? Yeah, let's go ahead and write that out explicitly. The opposite of 2 times. So that's the opposite of 2 multiplications of 2. Y'all tell me, what's the opposite of multiplication?
Division.
Division. So that means that this is division 2 times with 2. So it's like I'm going to divide by 2 twice. Excellent. So that means I've got divide by 2 and divide by 2. I need something to divide by. We always know there's a hidden number 1 in front of all these, so I guess I could place that there. And all of a sudden I've got 1 with 2 2's on the denominator and a cohesive story. It's a story. Negative exponents is the opposite of repeated multiplication, aka it's repeated division. Okay, so then we get more of our table filled in. What about 2 to the 0? That one always stumps people. Yes, I know it's 1. Why? Because people say there's no 2's, and I say, well, then why isn't it 0? Because I would think that if I had nothing, it would be a 0. What's going on? Go ahead.
That hidden 1 is still there, so it's 1 with 0 repetitions of 2.
Ah, there's a good way of doing it, right? We could say if this is the hidden 1 is still there, the 1 with no repetitions of 2. So we either leave it blank, but then I do have some people say, okay, then that means the 2 goes away, so maybe I put a 0 there, which is not true. So it'd be helpful if we had a story to back it up. See, 0 in this context is not talking about the number of times of repetition, because it's difficult to draw that. It could be, you got to stretch it a little bit, but it could be. It's better if you think of 0 as a balancing point. It's a balancing point. So that we could say, is it true that 2 to the 0 is the same thing as 2 to the 3 minus 3? Is 3 minus 3 0? Then I can always replace things that look different but mean the same, right? And then from here, I can say that means that I have 3 repetitions, and then I take 3 repetitions away. 3 repetitions of multiplication that I take away. That must mean that I have 3 repetitions of multiplication, and I take them away. How do I take away multiplication? With division. So that means I have 3 repetitions of division. So it's a balancing point between the multiplication and the opposite of the multiplication. And whenever I have the same thing divided by itself, so long as it's not 0, I get 1. And it's from this point that after we graph it, we will get a graph like that. Yeah.
And that also the same to could you also the same thing for 2 to the first?
2 to the first being what?
Like 2 first power, 1 exponent.
Could it be the same thing as what?
As the 2 to the 0 or 2, 3 minus.
As saying like I have 1 repetition of it?
Yeah.
1 instance of it? Yeah, it becomes again a little bit weird because like how do you repeat something 1 time without having it appear again? Like that language becomes a little weird. And so it really is, it's a combination of all these patterns and these stories of saying I have 1 instance of 2. Have I repeated it? Have I not repeated it? Have I done the opposite of it? How does that all balance? So long as we're in that storyline, it's all going to work itself out. It's all going to work itself out. Good.
So where does the 1 come from?
Which one?
The one that we were using for the story of
This one here?
calculation. No, the one that goes in front of the 2 to the exponent.
Yeah, like top right.
Oh, because again, it's just like a story. Let's start off with 3, right? 3 we all know as shapes like 1, 2, 3 units. We could call that 3. Would you all agree that this is 1 instance of 3? 1 instance of 3 written using symbols in algebra is 1 times of 3. So it always makes sense that if I have 10, it's the same thing as 1 time of 10, because I just have 10. And that if I have -5, I have 1 time of -5. So we can always use that as an instance of saying, what is it that I'm trying to actually adjust here? What is it that I'm trying to actually reference? Right? If it's something confusing, I can always talk about it as being one of those something confusings, and then it's one storyline where I have divided and multiplied. Good, yeah.
So that would be one instance of two instances of two.
Yes, exactly right. That's another way of looking at it. So if you want to talk about that, that's one instance of 2 times of 2. All right, here's 1 time of 2. Here's 2 times of those 2. So I get 4. You can always bring it back to the stories. You can always bring it back to the logic. You can always bring it back to the pictures. That's why I've given you that. Because I always want it to come from a place that you feel like I could explain this to a 5-year-old, right? I could teach somebody who wasn't here that day. Good. Okay, let's talk real quick. Domain. Is there a single x value that I cannot plug into this storyline? Can I repeatedly multiply as many times as I want off towards infinity? Sure. Can I repeatedly divide as many times as I want off towards infinity? Great. Can I talk about partial multiplications? That becomes a little bit weird. We usually call those square roots, like 1/2 exponent is a square root because I have one of 2 pieces that would multiply and get me back to the original. So we can talk about the in-betweens as well. We can talk about the in-betweens. We can talk about the negatives, the decimals, the fractions, the zeros. Everything works. So our domain is going to be everything between negative infinity and infinity. What about for range? If I take an object, like a cookie, and I divide it so that all of you get an equal piece, you will all get very little cookie, but we could all make it happen so you get something, right? If I then take that cookie and I try to divide it to all students of NIU, will everybody get a little cookie? Very small cookie, but they all get some, right? If I keep taking that cookie and I divide it amongst more and more people, people just keep getting less and less cookie, but they always get a little cookie, right? Do I ever get negative cookie? No. So what we see is that we have a range where I never get less than no cookie, not less than 0. And our multiplication, our repeated multiplication allows me to go up from there. So the range becomes 0 not included all the way up to infinity. Because you cannot get 0 by just doing division. You cannot divide enough so that something goes away entirely. It just gets smaller and smaller. You can, however, multiply repeatedly so that something gets larger and larger. Cool. Let's pause here for a moment. Any questions on this? Okay. I'm going to do this one briefly. If we have 1/3 and we are multiplying it by itself over and over again, 1/3 of 1/3 is bigger or smaller? Smaller. So I flipped the storyline. If I divide by 1/3, is that bigger or smaller? Bigger. So now I've got the storyline flipped where it still is if I have no instances of 1/3, that's going to be 1/3 of the 0 power. That's just 1. If I divide, that's negative exponents. That causes it to get big this time. And if I multiply, that causes it to get small. So you can graph these nice and quickly. Nice and quickly. But why does dividing by 1/3 make it smaller?
No, bigger.
Oh, make it bigger? Because again, it comes down to a story. Let's do a story. Let's do 1 divided by 1/3. That would be 1 divided into groups, each of which is 1/3. For example, 4 divided by 2 is 4 things. I divide them into groups of 2, and I get 2 groups. So if I have 1 divided by 1/3, that means I have 1 object. I need to split it into thirds so that I get a group, and then I count the groups. How many groups do I get? 3. So 1 divided into thirds gets me 3 things I produce. The story. It's always a story. Every single moment, every single time. Story, 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 story. All right, let's talk about some of these shortcuts, right? We got these as rules. Y'all know by now how much I love rules, right? Big fan of rules? Hate rules. Not a single rule in this class. I've pretty much gone through everything and changed the titles because whenever I say rules, you all get the impression that you have to do it because I told you to. There's a place for that. Anybody here going to go study law? Have fun with your rules, right? We all agree not all laws make sense, right? They're just rules. I don't want this class to be that. This class is logic. It makes sense to us or we don't do it. So for example, what about this one right here? We can do an example, like let's do 2 to the 5th times 2 to the 3rd. To the 5th means 5 repetitions of 2, not if we agree. Good. 2, 3, 4, 5. 3rd means 3 repetitions. So I'll put 3 more. How many repetitions do I have? 8. Do y'all need a rule for that? We feel pretty good. We can see it with our eyes. We can say it as a story. If I have 5 repetitions, and then I multiply that so that I have 3 more repetitions, I have a total of 8 repetitions. So what do we do between the 5 and the 3? We add them. Do we multiply them? No, because it's not what we're talking about. We're talking about instances, how many instances I count. So what we can say, to make this more general so that it relies less on the 2s, the 5s, and the 3s, is we can say, look, if I have a bunch of these A's, how many? Let's call it M times of A, all being multiplied. And I multiply that by N more A's, then wouldn't it make sense that I have M and N repetitions of A? It's a story. It's always a story. All right, what about this one? I've got A to the M. I'm going to let you all play around with some numeric examples. Let's just do like, if I have M repetitions, that means I have A times A, a whole bunch of M times. And then to the N power. Doesn't this mean I repeat stuff? So like maybe we should do an example. Let's do 2 to the 3rd to the 4th. That's 2 times 2 times 2 to the 4th. Do we all agree? How many 2's am I going to get if I expand this so there are 4 of them? 12 of them, because I'm going to be repeating the repeats. So if I'm over here and I say I've got M, and then that's all being raised to the N power, then I've got A, M times of N of those repeats. No rules. Now we can start to go through these quicker. If I have A and B and I repeat that 1, 2, 3, I repeat it M times, how many A's will I have? M of those A's, because I will have 1 in each of the parentheses. Great. How many B's? M of them. Great. And we get our 3rd rule, because we can just imagine it playing out through the logic. What about this one here? If I have A repetitions of numerator, let's keep in mind that on the numerator, that means multiplication already. Like for example, 2/3 is a story that says, of the thirds, I have 2. So 2 is my quantity. 3 is my size. If I cut this again, and I want to make thirds of thirds, that's cutting each of these thirds into 3 pieces. That would make it out of 9 pieces. So whenever I multiply on the denominator, I'm just making the pieces smaller. Whenever I multiply on the numerator, I'm getting more pieces. So let's imagine if I have A repeated over and over and over again on the numerator, M total times, how many A's will I have on the numerator? M of them. I'll have 1, 2, 3, as many times as I repeat it. And on the denominator, I will have how many B's? M of them. What about on this last one? Here, I've got a whole bunch of instances of A and a whole bunch of instances of A. What do you all want to do whenever you multiply and divide by the same thing? You want to cancel them away. That takes them away, right? It takes them out of the story. So wouldn't it make sense that at the end of this, you get M, but I've taken away N of the ones I canceled with? It's a story. It's always a story. Make it make sense, right? Fight for the understanding. It's so much better than memorizing. When I first started teaching, they're like, we have exponent rules. I was like, I'm sorry, what are they? And they were like, there are 7. You need to know them so you can teach them to students. And I was like, I have no idea what the 7 exponent rules are. I'm like, I can do exponent problems like no one's business. But like 7 distinct rules? Like, we need to memorize this? It's one storyline. I'm repeating multiplication. Sometimes I repeat division if it says to do the opposite. That's it. Been playing with that since we first learned about it. So the way that I like to model all these when I'm talking about exponentials, I like to model these as a pay it forward model. Anybody here know what I'm referring to when I talk about pay it forward? Like, I remember this coming up very, very little. Like, I remember like when I was exposed to this clip, it was an old clip. So the idea here is this kid's going to try to change the world by helping 3 people and hoping that they, through the honor system, help 3 people ahead of them. Instead of returning the favor, they pay it forward. That's the entire clip. The question I have for you all, how long until everyone in the world is helped? Let's assume that each of these kind of pay it forward instances happens 1 a day. We'll make it nice and easy, right? On the first day, we help 3 people. On the next day, we'll help how many people? 9. 3 times of 3, right? For every one of those 3, they've each helped 3. 3 times of 3. By the 4th day, we are at 3 to the 4th power. All right, that's 81. So by the 4th day, we are at 81 people helped. Based on the last time I decided to Google this, there are 7.5 billion people in the world. We got to go from 81 to 7.5 billion. Who wants to take some guesses as to how many days it will take? How long? 12? So we got 12? We think bigger or smaller? Go ahead. 30? All right, we think bigger or smaller? What do you think? Good.
Probably
10?
10.
40 or 50? I mean, this is the whole world, right? You all think that we're going to be like done to helping everybody within a month, 2 months, year? Where are we at?
Definitely less than 20 days.
Less than 20 days?
2.5 years.
2.5 years, sure.
Yeah, I think it's definitely going to be around the year range, like you said.
The year range, so 365 days. Let's start to test some of these, right? So let's go ahead and do 3 to the x, because that's how many days are going by, right? This is our function, our exponential function, our pay it forward function. We can check this with different x values. Let's do x equals 10. 3 to the 10th. Who's got a calculator? Let's punch this out.
590,000.
590,000 ish. All right, good. Long way to go until billion. Billions with a B, big billion. All right, so let's try f of what would be a year? 365 days?
Is it overflow error?
Overflow error. Too big. Too big for the calculator to handle. Oh, okay. Let's try 30. What do we get for that? What do you have?
21.
You have 21? 21. All right, what's 21 come out to be? 1.04 times 10 to the 10th. Does yours have a little e? Some people's will have a little e like this. That just means times 10 to the. So we can say this 1.04 times 10 to the 10th. But don't worry about it too much. Let's remember that million was 6 zeros, billion was 9. This is 10 zeros. So it's a 1 and 10 zeros. I guess, yeah, that's a 10 billion. That's a little over, but pretty darn close. And I bet if you typed in 20 instead, you're a little under. So it's about 21 days. Can you imagine that? In 21 days, that process would touch every person on Earth. Now, here's the interesting part. If you take that and you start bringing it back to some other things, anybody here heard of like multi-level marketing schemes, right? Or the scheme, multi-level marketing organizations? Sure, I don't know what I can say about that. I know that when I was an undergrad, I worked for one because they recruited me, right? And it was a good way to make some money. Or at least that's what they told me. They said, you go get 10 friends are going to sell, you're going to make some money off them, they're going to get 10 friends, et cetera, right? And it was like, good, if I do that, I can get a whole bunch of people, make me a whole bunch of money. Let's run that through the math real quick. 7.5 billion has how many zeros? 9. That means that between the CEO and me, there can only be 9 people, 9 layers playing this game until we have literally sold knives to everybody on the planet. Not to mention, most people don't want my knives. Most people can't afford the knives. And I've got a whole bunch of people in my neighborhood, my age range, that are also selling the knives. Like it's a challenge when you realize that like these are overpromised situations, that they explode too quick. They explode too quick for everybody to be able to get 10 people. All right, so on that idea, recognize also from our graphs that on our graphs, our exponential graph, whether we drew it the first way or the second way, first, is it a function? Who can tell me why and how they recognized? Yeah, good.
For every X value, you get 1 Y value.
Very good, right? If I said I repeated this pay it forward model for 5 days, do we all think there's going to be a certain number of people I helped, or will it be a little unsure? Certain number, right? 3 to the whatever is going to get me a number. That's a function. If I lock in, I start a place and it transforms me to an answer, no ambiguity every time, that's a function. How can we recognize it with here? Somebody else. How can we recognize it visually?
Vertical line test.
Vertical line test. It's passing the vertical line test at every single point, because remember the vertical line test is just a way of me taking an X value and recognizing there's 1 Y that goes along with it. Does it pass the horizontal line test? Who can remind me what the horizontal line test means? Someone else. Let me throw it around.
It means that the inverse is a, so if you do the horizontal line test, it means that if you were to do the inverse, that would also be a function.
Good. It means if I do the inverse is going to have a graph like this, whatever it is, that there's a way for me to be able to take the number of people I helped and backtrack it to what day I'm on. Doesn't that make sense? Shouldn't I be able to say I helped this many people today? And we can be like, oh, you've been running the pattern for this many days. So if I have the ability to backtrack it without ambiguity, then it's going to pass the horizontal line test, because that's really what we're doing, is we're taking all of these outputs of people helped and bringing it back to the day I helped them. So we have this ability to undo exponents. I call these operations of undoing exponents, I call them power finder functions. Because really that's what we're trying to do. We're trying to find the power because we're trying to figure out what day we are on in the process. Like for example, if I say 3 to the X is equal to 81, what is X? Think it through. 3 times 3 is 9. That's on the second day. Third day, I would be up to 27. Fourth day, I would be up to 81. So X must be 81. How did we do that? Well, we did some kind of analysis of trying to figure out what that power is. Watch how I might notate that. If I had no textbook in the world to tell me what to do, and I was just trying to figure it out, I might say, you know what I'm going to do to both sides? I'm going to do a power finder. I'm going to do a power finder to both sides. I'm going to find the power. Right? Or better yet, let's even make it where I just do it overall. I'm going to find the power of this whole thing. That means at the very end, I have X, and then I'm going to find the power that turns 3 into 81. I could make a notational system that describes this. It says, I'm trying to find the power. It's a sentence, right? I'm going to find the power with my power finder function. I'm going to find the power that turns 3 into 81. Now, textbooks don't call it power finder functions. What do textbooks call it? They call them logarithms. Logarithms are literally power finder functions. It's all they do. They just find the power that goes along with the story. And so we'll spend a little bit of today just to kind of introduce it. Tomorrow we'll spend more time on it. We're not done yet, don't leave. But I do call them power finder functions. So whenever you say logarithm, again, my job as a teacher, I'm trying to give you simple concepts that make sense to you that you can replace the new words with until the new words become comfortable. Derivative, we replace derivative with change or slope. Slope is better than change because change could just be subtraction. Slope is best. Or in the real world, speed, right? Any of those are great models to help us kind of make sense of it as we build up familiarity. What about integral? Integral goes with area or total, right? So that works out. Limit is the logic of close, only if I'm going in that direction. We could just say approach. How about logic of approach, right? Like I'm trying to approach something, trying to figure out what I get close to. So we get simple ideas, right? Try to make simple things and then build back up into the language. It's totally fine. So here, if I ever say logarithm, we will think of them as power finder functions. Or I've also got a second model that I like to use. I'll bring that up tomorrow for you to be able to take a look at. But let's just do an example here again. Let's imagine that I have this scenario. 4 to the 3x is equal to 16. Do we want to find the power? Yeah, so we might as well use a power finder function. Can we agree on that? All right, so let's do that. Let's go ahead and do I'm going to find the power that turns 4 into 4 to the 3x. And because I do it to one side, I will do it to the other. It's got to be the same power that turns 4 into 16. Notice cohesive story. If I turn 4 into 4 to the 3x, then I've used a power of, take a look here, break it down. Find me the power that turns 4 into 4 to the 3x. 3x, it's the power, right? It's the power that made that transformation happen. So this entire thing is 3x because it says find the power that turns 4 into 4 to the 3x. Well, that power is obviously 3x. What about over here? Find the power that turns 4 into 16. What would that be? 2. And then from here, it's just simple, right? Watch how that appears if you want to use what your textbook says. They just do log base 4 of 4 to 3x because that's what a logarithm is. Log base 4 of 16. We know that's a power finder, so I find the power that turns 4 into 4 to the 3x. That's got to be 3x. To find the power that turns 4 into 16, that would be 2, and we get the exact same answer. So moral of the story, I have spent years of my life searching for easy pictures, good word substitution, and stories to make sense out of these difficult concepts for you. If any of these are not something that you understand from a place that means like you could explain it, you got like it makes sense, then just invite me into the conversation. I will happily explain more. But don't accept anything as a rule. It's not. This just is not the topic for it. If you have any questions, feel free to stick around. Again, don't ask about the test. I don't have them. Nick does, but I'll be available to talk about them after you get them back in your discussion sections.